was either the first guy or the last guy. Yeah, it sounds good. Yeah. I just walked up to the thing. I know. Well, and they had they had like, okay, I would have been totally go bold. Oh, yeah. It's what's the way that what we don't have the place forever. Yeah, that's up to you. He's there.
I was gonna say, yeah. They're not set, right?
Drive the rest of the way. 2 hours to us. Yes, we're like, so she's like, so great. Like, but we're joking like, that they're.
Hey, let's get going.
They are bumper stronger.
So everybody looks refreshed. Hopefully you had a good break. So I got the exams have been graded and I posted the grades. I'll return them next time. We still have a person that needs to take the exam. They couldn't make it last time, so I don't want to turn the exams until we get that all taken care of. It should be done by next time, so I'll return the exams next time and we can talk about it. What I want to do now is switch gears a little bit. And we're going to spend the next, I don't know, couple of weeks anyway, talking about wells. And wells are an important aspect of hydrogeology because that's how we understand what's in the subsurface. Well, one of the ways, one of the important ways. There are some other geophysical techniques that are also used. The wells will be an important technique. It's really the way that we're gonna be able to get samples of the water in aquifers. And it's the primary way that we measure pressure. So we'll be talking about various things, the types of wells and how they're created, the different conditions that require different methods, and then there's some the basic approaches to shown here, and take a look at some of the commonalities and differences. Okay, so put up here at the top to check out some videos. So a couple of years ago, I went through and found some videos on well drilling, and they show some things that are hard to demonstrate in the classroom, like how drilling rigs work. There's kind of a cool video of a couple thousand feet of drill steel getting shot out of a well from overpressure. So that's something hopefully nobody has to deal with, but pretty interesting video. So check those out. So this is just the start of the topic here, was just kind of an overview. These are the things that we use wells for. So we can use them to pull fluids out of the subsurface. And in hydrogeology, we're going to be primarily interested in water. But in environmental applications, we also will be pumping out NAPL. That's an acronym that stands for non-aqueous phase liquids, like gasoline and oils. Those are liquids that are not aqueous phase. If you put a well in the vadosome, you can pump air out and also vapors. And then some wells are designed to remove heat or put heat in the ground, heat exchangers. Okay, so that's another application. Well, I guess it's recovery, it would be pull heat out. We also want to put things in, so water and air are injected. I guess we also can inject heat. We have a project going on right now on campus where we're injecting some very high heat at very high temperatures. We're heating the ground up to about 200 degrees C. So using wells. So that'll be a type of injection. And then also we'll be using wells to monitor what's going on in the subsurface. So we've talked a lot about hydraulic head. The way we measure it is with monitoring wells, and also we take samples for composition. So we'll see some of the details about wells and how they're built. But basically, it's going to be a pipe that's in the ground, and you can see here. This is a monitoring well that is looking down on it. Here, this is a manhole cover, and this is the pipe, the casing that is forming the well, and it's got this vault here, and it's covered with that cap, so it's flush to the ground surface. So if you want to drive around and have it in a parking lot, say, you can do it with a flush mount like this. In other cases, wells are sticking up. The pipe that's forming the well, the casing is sticking up. Here's a very simple water well, a pipe coming up like that, and the water coming out. Could be more sophisticated though. This is down in Mount Pleasant. There's a water supply well in Mount Pleasant that they use to pump water out. They also use it to put water back in to recharge the aquifer. And the well itself is over here, and then this is some of the distribution pipes. This is a SVE well, that stands for soil vapor extraction. Talk about that later, but that's where you pump air out of the vadosome and circulate air through the vadosome in order to recover contaminants. And this is a well here, and it's got piping going to a manifold. So there are a variety of wells. Actually, these are all wells going to a manifold for SVE. So it's getting a bit more sophisticated. Here's an even more sophisticated one. This is a geothermal well. There's a person here, so this is a big, lot of hardware here it's servicing this quite deep well that's pulling out fluids that are very hot, so it's insulated and getting fairly complicated. All right, so all of those have the basic procedure in common. So in order to create a well, these are the main things you have to do. You're going to do some drilling. You're going to make a hole in the ground. And maybe as you do that, you're going to take samples of the material that is coming out as you make that hole. And then the act of going from a hole in the ground to a well is called completion. So that's where we put in the pipe or a casing and a screen and filter pack. And that turns it into a well. Basically, what we need to do with the pipe is put that in there to hold the hole open so it doesn't collapse. And also provide some filtration for removing or filtering out fine-grained particles when we pump water out. So the next step here is development. And when we first drill a well and complete it, there's often a low permeability zone between the well and the formation. It's a result of how the well is drilled. So if we want to use the well to pump out fluids, that low permeability zone is going to cause a problem. So there are methods for removing that low permeability zone, and doing that is called development. Okay, so once we're done with that, the well is ready to go. And if we're going to be pumping out water or oil or liquids, then typically what's done is to put a pump down into the well. There are other applications that we saw for vapor extraction where you can have the pump up the ground surface. and just apply suction, but for the most part, for water wells, there's gonna be a pump that goes down the well, so you can push the water up instead of lifting it by suction. So we have to install a pump, and once you do that, you can turn the pump on and start pumping water out, and get ready to use the well. So that's the overview, and here's the detail. So for drilling, in order to drill a hole in the ground, we have to do these three things for the most part. So we have to be able to cut the formation. So we have to break it up into pieces that can be removed. And then we have to remove it. And in some cases, we have to stabilize the hole and prevent it from collapsing. And if we made the hole and it just collapsed before we could do anything, that would be counterproductive. Okay, so the details of how we do this will vary depending upon what material we have in the subsurface. So here's a little video. So this is the drilling technique, cutting the formation, and then removing the cutting. They have to break it up, and then you have to get that stuff out of there in order to advance the depth of the hole. And then you have to do something here to keep it from collapsing. Okay, so there are various different methods for doing that. Depends what it is you're trying to go through. These are the most common methods that are used around here. They have different mechanical aspects to them, and they're used in different materials. So direct push, augering, air hammer, and mud rotary are the main ones, and they have different materials that they're used. Direct push is used in saprolite or sediment. Augering is used in saprolite also or in sediment. Air hammer and mud rotary are techniques that are used to go through solid rock. Okay, so we'll look at each one of those. Direct push. So as you might guess, this involves taking a drilling, basically it's a piece of pipe, and just pushing it in the ground with a hydraulic press. This thing here, got a big hydraulic cylinder to push this in. There's also a hammer that works like a jackhammer. So you can push this in, and it has a point on it. And as you push it in, it pushes the material that it's going through aside. So this is a bit of an exception to the rule that to the process that I showed on the previous slide, because in this case, you're making a hole by displacing the material that's there, and you're not actually removing any material. The reason that's important is because this technique is the most common one for sampling at shallow depths and contaminated ground. If it's contaminated, you want to get samples out that you use for evaluating the contaminants that are there, but you don't want to have a lot of other material coming out that you have to deal with. So this is commonly used for shallow depths environmental assessment. Many of you will use one of these rigs in the next, I don't know when are you going to graduate? If you get a job in the environmental business, you'll be using one of these. These are really common. There's a variety of details about how they work. Here is a sketch of this is a screen. So this is a pipe with slots cut in it. So this gets pushed in, and then water samples are recovered from this. And there are a variety of other types of tooling that you can get for taking soil samples, as well as water samples. So it's good in sediment, saprolite. You can create small wells, get soil samples, and you have no cuttings. But the limitation here is that you're taking a piece of steel and hammering it in, and so it's only going to go through soft material, sediments, saprolite. It's not going to go through rock. And so if you have even a fragment of rock like this in some saprolite and you hit that, it's pretty much going to stop. Okay, so it has limitations in terms of the depth that you can reach. Okay, it also has some limitations in the hole size. So if you need to make a bigger hole, and typically if you're going to make a well that you want to pump out of, then typically that's going to be require a bigger hole. So the typical way that that's done in material that is soft, like sediment or saprolite, is to use an auger. And so here's a picture. It's got a spiral on it, and the cutting head is here. So it rotates, and these cutting teeth, they're coming in at an angle like that, and they're hardened steel, and they're going around and scraping the sediment or the saprolite. So they're breaking it into particles just basically by scraping it. And then the sediment is removed because it gets conveyed up this auger as it rotates. So that works pretty well in material that is soft. You can make a big hole using this. Here's a pretty big auger. These things are made, sometimes this is a solid piece of steel, but a lot of times in this case, it's a hollow tube. So you have another piece here that can go inside. And then as you drill, this is inside and this is blocking the hole. But then you can pull this out, and the soil is exposed here at the bottom of this tube. So you can take a sample down through this. Here's an example of how that would work. This is a sampler that's going down below the bottom of this. This is called a hollow stem auger. And this is also very widely used for geotechnical investigations, for environmental investigations. It's limited in the material that it can go through, and somewhat limited in the depth. But these kinds of depths and this kind of material are very common. So you see these rigs used a lot for many applications. So for those of you going, well, if you're going into environmental or geotechnical, we will be working with one of these rigs. This is auger drilling, and in particular, this is a hollow stem auger. Okay, so the hollow stem auger is working by shearing. That blade spins around, or the cutting face spins around, and it's cutting by shearing the particles. So if you try to do that with rock, you're going to break the drill bit, because it's very difficult to cut rock in shear. So for drilling through rock, the way that that's done is by crushing it in compression. So the device that's used, one of them is this thing here. That's a cone with a lot of bumps on it here. And these bumps are carbide, so they're very hard material. And as you rotate this bit, these cones rotate. So as you rotate around these cones, the cones are rotating as well. So what's happening is the cones are kind of doing that. Well, let me see for people online. The cones are kind of going like that. And so each one of these hardened carbide nibs here are getting pressed down into the rock. And then as it gets pressed down, it crushes the rock underneath it. So you break the rock by crushing, you're not spinning it around and shearing it, which would wear out the bit. So everybody heard of Howard Hughes? Heard of him? No? No? Okay, so he was a rich guy back in the day, and he made a lot of money by inventing this kind of a bit. This kind of a bit was developed back in the early 1900s, and this is really key to be able to drill deep wells for oil exploration, for example. Because if you try to cut rock by shearing it, the bit is going to wear out quickly, and you're going to have to pull it out. And if you have to do that often, and you're trying to drill a deep hole, it's going to be really expensive because you're always replacing the bit. This thing lasts a lot longer, so you can drill a lot deeper and a lot further before you have to replace the bit. Okay, so that is that's one style of bit. For rotation, it crushes the rock, and then to get the cuttings out with this kind of a bit, there's a mud that is injected down through the drilling steel and out through the bottom here. That mud picks up the particles of rock that have been crushed under the bit and brings them up to the surface. So that's called mud rotary. So the rotation causes crushing, and then the mud removes the particles. The other way of doing it is to have a bit that is flat with carbide bit bumps on the bottom of it, and it's going up and down. So it's powered by something that works like a jackhammer. So it goes up and down. As it goes down, it crushes the rock. And then it's powered by air. And then the air is vented out the bottom, and the air is going fast enough to bring the particles of rock out as kind of like sandblasting. That's called an air hammer. So these are both techniques that'll go through rock. Mud rotary, this is used for unstable formations because the mud that's used to remove the particles is also stabilizing the hole. So in order to keep a deep hole open, you have to have pressure to counteract the stress from the rock. So if you have a situation like this, if you're drilling a deep hole, the stress in the rock is going to tend to make that hole come in and collapse. So you need to have something to counter that. And if you put water in there, that creates hydrostatic pressure, right? But this is from this stress in the rock will be at least from the lithostatic pressure, lithostatic stress. So rocks are denser, the unit weight is greater than of a rock is greater than water by 2 to 3 times. So this is going to be greater than that if it's water. But if you add mud to the mix here, that increases the density and helps stabilize the hole because it increases the stress that's countering this stress that tends to make the hole collapse. The other thing that mud does is it forms a filter cake here, so you don't have a lot of fluid flowing out of the well. So that can be good if you're drilling through sand. You drill through sand and you had water circulating, the water would just flow into the sand. and you would lose all the water that you're trying to circulate. So the mud forms a filter cake, which is good if you're trying to drill through sand. But once you have the well finished, that filter cake could will form a barrier to flow. So that will be something that we would need to remove with development. Air hammer is going to be good in rock that is stable. So you don't need to have as much support as you would with mud. This is also going to be good in a shallow water table if you have if you're drilling with air and you have to have the hole filled with air. So if you have a shallow water table and a lot of water flowing in there, then the air has to remove that water. That can be a problem. And yeah, so here's that mud has a useful purpose, but it also can cause some problems. If you have air, then you don't really have that kind of impact on the building. So here's what some of that stuff looks like. Here's a picture of a bit that's used for mud rotary. You can see the cone there a little bit better. There are 3 of them. So it's a tri-cone bit. And then this is also a bit that goes on the outside of a casing there. And these are also carbide. This is what an air hammer looks like. This is the bottom of the bit, and these are carbide. So this is what it looks like. The carbide is down here. This thing goes up and down. The hammer is up here. So you've got this big, you got basically a weight that's moving up and down really fast from a high flow of air. And that moves this up and down and crushes the rock. And then you have air coming out here at really high velocities. And that just entrains the crushed rock and brings it out to the surface. What you see at the surface is a very high flow of air with a lot of particles in it. So it's very abrasive. And they kind of direct it out, it shoots out, I don't know, 20, 30 feet, 40 feet. Here's an auger rig. You can see the auger there. This is air rotary rig. That thing there is a compressor. So in order to do this kind of drilling, if you're gonna drill a hole that's a few hundred feet deep with air, you need to have a really big compressor, and you need to have a mast for hoisting up the drill steel and lowering in the hammer. And all these things are direct push. Geoprobe is the company that developed this technology, and there are a variety of other companies that make these kind of rigs now. Geoprobe was credited with developing it, and so their name is often associated with this style of drill rig. We actually have a drill rig like this, the Geoprobe rig, and it's on tracks. You can drive it around, and then this is the mast. So this comes up, and it looks like this when it's in use. There's another picture. So, about these various different techniques, they have different constraints, the different materials they can go through, different depth limits, and different cuttings that they produce. Mud rotary, this is the technique that's used to drill oil wells. It can stabilize the formation and also remove cuttings from great depth, so it has the deepest depth limit. Okay, so we can make a hole. Now we got to complete the hole. So probably the most common technique for creating a shallow well looks like this. You've made a hole here using the drilling technique. This It might be well, any of those techniques that we saw, the auger or air rotary. And then this is going to go in the ground, in the hole. So there's two pieces here. This is the screen and the casing. So the casing is similar to a piece of pipe, but it has special threads on it. In most cases, that differ from the threads that are typically used on pipe. And then this screen is similar to the pipe, except it has slots cut in it to let the water in. So what you need to do now is support the hole, and there are, if this is a porous material, there are particles in here that get mobilized when you pump water out. So you need to stabilize the hole so it doesn't collapse. And you also need to filter these particles out. So the way you do that is to put sand in here in this annular space that fills up the hole and prevents it from collapsing. This sand acts as a filter. So the sand will filter out the small particles that are mobilized, they're mobile here, like clay particles, right? It'll filter those out. And then the screen here, these slots are small enough so that they filter out the sand. It's kind of a two-step process. And so you have to size the particles, the filter pack here to hold back the particles in the formation, and you have to size the screen to hold back the filter pack material sand. So now what you need to do is seal up this annulus. So the way that's done is to put in a material called bentonite. Bentonite is composed of, it's a rock that is composed of a clay mineral called montmorillonite that swells when it's exposed to water. It'll swell several times larger than it is when it's dry. And as it swells, it fills up the pore space between you get chunks of bentonite, and it swells up and fills up the pore space between the chunks. Forms a very low permeability plug here. And then on top of that, you put cement grout. And so what this is doing, the bentonite in the grout, that's sealing the annulus, so contaminants appear at the ground surface, and there are lots of contaminants at the ground surface. The primary one that you don't want getting in your well is, when you're going out walking your dog, their dogs have been walked many places, and if this dog has been walked near your well, you don't want that getting down your well. So this has been, that's what this seal is to prevent surface contamination. So you have a grout seal, bentonite seal, the sand filter pack. So this is the action. Sand filters fine sediment, particles from the formation, well screen prevents. So there you go. Stop that from happening. Okay, so here's some pictures of the screen. This is what it looks like, where there's a casing and a screen down in the well, and then this is the filter pack being applied here. And one of the things here in this example, what this is showing is the screen and a filter pack. And I don't know if you can see this, but there's a gap right here. So this might happen if the material you're putting here in the annulus shrinks. So if it shrinks, then it pulls away from the casing, and there's a gap right here. This is a crack in the angular seal, and this is a place where when you put the material in from the top, it bridges and doesn't reach the bottom. So all of these are problems because they compromise the seal. And it means that the water that is getting pumped out here isn't necessarily coming from right here. In this case, there could be contaminants coming from the ground surface. Here with bridging, there could be contaminants coming up from here shallower depth. Many of you going into the environmental business will be working with drill rigs. One of the common things for entry-level jobs is to supervise the drilling process and to supervise this completion. And one of the responsibilities that you'll have is to make sure that things like this don't happen, that you don't have bridging going on. Okay, it can happen very easily, and you'll need to be responsible for making sure that it doesn't happen. Okay, so when the well is completed, you need to select a size of sand that filters out the particles in the formation, and is also prevented from entering the wells by the well screen. So there's a variety of different grain sizes of materials that are available for well completions, and you would select that based on the size distribution of the particles in the formation. Okay. So talk about how to install the gravel packer. Let me show you some of this stuff. So a well is going to consist of a casing and a screen. The casing is a solid piece of pipe like that. This is a 2-inch piece of casing. And then the screen has slots cut in it like this. So these are very narrow slots, about 0.010 of an inch. And in this case, these slots are cut with a circular saw, a whole bank of circular saws that go down and cut that set of slots right there. Wells are typically completed with casings that have thread that look like this. This is called a flush joint casing because it screws together like this, and there's no enlarged piece here. If you buy pipe from Lowe's and you want to couple it together, there's a coupling that is enlarged. And if you go to Lowe's and you want to couple together pipe, a common way to do it is to glue it together. And even if if you screw it together, you're using fittings that are glued on. Okay, so the common way of joining pipe, PVC pipe, involves glue. That glue has solvents in it that are carcinogenic. Okay, methylene chloride. So you don't create wells with pipe that you get from Lowe's with glued together fittings. You use casing and screen like this with these flush joint threads. These are more expensive, but they go together and form a seal without requiring glue. There's a groove right here and an O-ring goes in there to do the sealing. And so it screws together with an O-ring seal. Take a look at that. Here's another one of these flush joint threads with O-ring in place, and this is just about 1 foot long, but you can see that these slots are cut over the full length, and that's another example. So one way to cut the slots is with the circular saw that goes down and cuts. This is just basically a piece of pipe that where these slots are cut with a circular saw. Another way of doing this, you're welcome to hold it. Yeah. pass it around. So there are other designs. Here's another piece of screen that has, it's configured with a little bit of a different geometry. It has these ribs on the center, down the mid or down the inside to give it extra support. And then it has a much larger area where the slots occur. So this gives you a lot larger area, open area for fluid to flow into. Here's a bigger version of that with the internal ribs. This is patterned after a wire wrap screen. That I'll show you just a second. So those are all examples of PVC pipe used as screen. And they're not the cheapest way of doing it. Many wells utilize that technique. If you want to go with, well, in environmental sites and then also with water wells, they're often using wire wrap stainless steel screens. So here's basically the same design where there are ribs on the inside of the screen, and then the way this is done is that there's a wire that is shaped like this. So there's the wire with a cross section. It look like that, and it's wrapped and like this. So this wire cut, and so there's a very narrow gap right there, but it expands out. So it's a narrow gap to block the inflow of particles, but it expands out like this to reduce the head loss during flow. So, and then at each point where the wire touches the rib, it's welded. Okay, so this is called a wire wrap screen and stainless steel. So this is like the Cadillac of screens here. Very, very high amount of surface area, and it's got this custom made shape. It's also the most expensive. So here's just a little wire wrap screen, little small one. And then we talked about the materials that are used to create wells. So bentonite is an important material because it forms the seal. So I'm going to send around two, I guess we'll go different sides, but these have these gray particles in them. This looks kind of like gravel, and this looks like sand. But these are bentonite. Bentonite is clay. Clay is very, very small particles. You can't see clay particles with your eye. So this is bentonite, many clay particles pressed together and dried and broken up. Okay, so you use bentonite like this in these chunks because you're gonna dump it into the well, the annulus. You want it to fall down to the bottom. If it was powder, it wouldn't make it to the bottom. It would just stick to the side. So you use particles like this or like this that are large enough to fall and make it down to the bottom of the annulus. Now, what I don't have, sometimes I bring a cup of water and we hydrate this stuff, but I don't have that this time. This stuff, when you get it wet, it turns into this, it's very sticky and low permeability material. And then the filter pack is sand that is screened to be a particular grain size. You can get many different grain sizes depending on what size you need to filter out. This is an example of a medium grain sand, kind of a typical grain size that's used for wells for the filter pack. Now. That sand that's going around, that would be an example of a filter pack or it's called a gravel pack. And in order to get the bentonite and to get this gravel pack down into the annular space without bridging, you know, if it's a shallow well, if it's 10 feet deep, you can just drop it in from the ground surface. But if it's 100 feet, couple 100 feet deep, if you try dropping it into the ground surface, it's not going to make it to the bottom. So the way that it's done is this is a pipe here that goes all the way down to where you want the sand to be, and a funnel, and so there's water going in here and washing down the pipe, and then sand is added. This thing here, this pipe that goes down is called a Tremy pipe. And conveying the sand down the Tremy pipe is how you get it to go down to the bottom. Here's this stainless steel wire wrap screen going in, and then the gravel pack being added using a Tremy pipe. So yeah, here's how it works. There's a funnel and it goes down and it's flowed like that. Okay, so that's how wells are completed in unstable material like saprolite around here, or sand, gravel. When you drill a well in rock, in crystalline rock though, crystalline rock is stable enough in many cases, so you don't need to have a well screen to hold it open. If you just drill a hole, it stays open. So wells that are drilled in rock, they go through saprolite, and then you need to have a casing here when you go through saprolite, and that casing is sealed in here with cement. But then you go inside the casing and drill a hole down inside the casing, and that hole is just open in rock. So this is called an open hole completion. And if you look down one of these wells, look like this. This is the rock here. This is one of the wells we have in over in the Botanical Gardens. And then this is where that well goes through a fracture. So you're looking down on it, you can see the fracture wrapping around the well. But remember, the flow in the fractured rock, the flow into the well is all coming through fractures. We did a project a few years ago where we put a camera down the well and spun it around and then stitched all the photos together. And here you can see that kind of sinusoid. That's a fracture that's dipping. And this is the image of the inside of a well that has been unwrapped. Like that. So what I just showed you was a well that looked like this. But remember, like on the exam, we had wells, well A and well AL. So wells are often made in clusters where they measure they're completed at different depths. So here's a cluster of 3 at different depths. And these are different wells. You can also go and drill a larger diameter well and have wells at different depths completed inside of the same hole. So here's a multi-level well. And you could do that various different ways. Here's a bundle of tubes that are put into a well. And this is really kind of the Cadillac, where this is a pipe here, and these are inflatable bladders that are inflated and sealed. And then there are ports that you can open and access the formation here at different elevations. So remember, early on when I would draw a well, I think I was just drawing it like this. If you remember that, so that's this. This is the screen here, and then this is the casing. So now getting into a little bit of the detail of what I was showing there. Okay, so in order to get this well to work, we need to, in many cases, develop it. So the way that that's done, the simplest way that a lot of drillers do is they just put a pump in the well and pump water out until it comes out clear. That doesn't really mobilize fine grained materials that are stuck onto the formation. So there are more aggressive techniques. One technique called airlift is to put a pipe down the well, hook it up to a big air compressor, hold on to the pipe, and where you strap the pipe down, and then you hook it up to a big air compressor and inject air really fast down below the water. That shoots all the water up in the air and removes the water very rapidly. So here's an example. This is a test that we did. Looks like a geyser. Removes the water very rapidly, and then the water flows into the well rapidly, and that removes the fine particles, mobilizes the fine particles that are in the formation, and cleans up the formation. Another way to do it is to take a block called a surge block, and it seals into the casing. You move it up and down, and it's kind of like a plunger, plunging a toilet, right? You move it up and down, that pushes water in and pushes it back out and mobilizes fine particles. So that gets the particles mobilized and hopefully out. Here's a surge block. There it is, and it's a heavy thing that's getting hoisted and dropped down into the well. This rig. So that's the development process. One thing that happens is as wells are operated, the screens can get clogged, and the formation around the screen can get clogged. So there are processes that are called redevelopment, where you go in and you try to remove the clogging material. Here's an example of a screen where there are precipitates here that are clogging up the screen. So this would, I think, have some pretty big problems with getting water to flow through this screen. So you can do surging, but for things like this, typically what would be done would be put in acid to dissolve away the precipitates. So ultimately then what you want to do is have a well that's completed with a casing and a screen and a filter pack, and the particles or they're all free from particles, and the formation around the well has also been cleaned out, so you can have flow to the well with minimal head loss. So that gives you access to the formation, allows you to remove fluids, add fluids, measure the hydraulic head, and we'll talk about what you can do with that capability next time.